At first light, Devil's Tower does not look like a mountain. It looks cut. A sheer cylinder of stone rises out of the Wyoming plain with a top that feels less eroded than interrupted, as if something enormous once continued upward and no longer does. The sides are furrowed in long vertical bands. The base spreads outward in a rough flare. Broken columns lie around it like splinters thrown from an impact no one recorded. It is one of the most photographed landforms in North America, and that may be the strangest part. We have looked at it for more than a century. We have named it, mapped it, measured it, and still, in the first second of seeing it, it presents itself as something the standard categories do not fully calm. The accepted explanation is familiar. Devil's Tower is said to be an igneous intrusion, or the hardened core of a volcanic system, exposed after the softer rock around it eroded away. The vertical columns are explained as cooling fractures, a known geological process called columnar jointing. Similar, smaller formations exist elsewhere. Mesas are remnants of layered rock protected by hard capstone. Buttes are what remain after mesas erode. Petrified wood forms when organic material is buried, mineral-rich water enters, and the cellular structure is slowly replaced by stone. This account is coherent. It is taught. It is printed in park literature and geology texts. For most people, it is enough, but the official explanation begins to feel incomplete the moment the eye starts comparing forms instead of names. Why do so many isolated formations resemble truncation more than uplift? Yet why do some rise with the proportions of severed trunks, not ridges pushed by tectonics or cones built by eruption? Why do they so often appear alone, detached from any obvious system, as if the surrounding landscape has been cleared away rather than naturally composed around them? And why does the language of common people, long before they knew the approved terms, keep drifting back to the same image? Stump, post, pillar, trunk, petrified wood, cut stone, giant remains. At what point does resemblance stop being coincidence and become a clue? There is a theory, usually dismissed before it is examined, that some of Earth's strangest isolated mountains are not merely rock formations in the ordinary sense, but the lithified remnants of a vanished arboreal world on a scale modern biology no longer permits us to imagine. Not every mountain. Not every mesa. Not every column of basalt. The claim is narrower and more unsettling than its caricature. It suggests that a subset of these formations may preserve the structural geometry of once living giants, later mineralized, fractured, buried, exposed, renamed, and absorbed into geology, because geology had no other accepted category to place them in. It sounds impossible. So do many things until the record is forced to hold still. Start with shape, not symbolism, not folklore. Shape. A living tree trunk widens at the base where stress is distributed into the ground. Engineers call it load transfer. Carpenters call it common sense. In large trees, this creates root flare, a visible expansion near the base. Many so-called stump mountains display an exaggerated version of that same transition, a cylindrical or slightly tapered rise, then a broader footing, then a ring of debris around the perimeter. Devil's Tower is not just vertical, it is vertically organized. The same is true of numerous table mountains and buttes, whose sides descend in straight or slightly fluted planes from a flat upper surface. The pattern repeats in forms too blunt to be called peaks and too abrupt to feel like ordinary ridges. They look less like things that grew from below and more like things that were left behind after being cut above. Then there is the top itself. Mountains formed by uplift and long weathering often carry irregular crowns, broken ridgelines, drainage scars, and the asymmetry of stress. Many suspected stump formations do not. They terminate in platforms, flat, level, sometimes astonishingly level relative to their mass. Geology explains this through caprock and erosional resistance. That is the standard answer. But a flat top is also exactly what one expects from a severed trunk if the cut surface later hardens, fractures, and sheds. What matters is not a single example. What matters is the recurrence of this geometry across regions that share no obvious cultural myth, but display the same visual grammar: abrupt vertical body, broadened base, flattened crown, and surrounding fields of angular debris. The sidewalls deepen the problem. On many of these formations, the vertical texture is not random, it is directional. Long parallel lines run from top to base, resembling fibers, grain, or elongated cellular structure translated into stone. Mainstream geology points to cooling cracks in igneous material. In some places, that explanation is persuasive. Hexagonal columns are real. Basalt does fracture that way. But not all vertical striation is clean hexagonal jointing, and not every stump-like mountain is composed or situated like a classic volcanic remnant. The visual resemblance to wood grain is not proof. Of course, it is not. But when the resemblance appears alongside the stump profile, the flared base, the flat crown, and the isolated placement, the probability of pure visual coincidence begins to weaken. The official explanation deserves to be taken seriously, because parts of it clearly work. We know stone can preserve forms that were once organic. Petrified forests are not myths. Entire logs have mineralized. Cellular structures in ancient wood have survived replacement by silica and quartz so precisely that growth patterns remain visible under magnification. And as the record shows that organic matter can become stone without losing its architecture, that matters. It means the central objection people often raise was trees do not turn into rock is simply false. They do. The real objection is scale. Modern petrified wood is familiar at the scale of fallen trunks, upright stumps, and buried forests. The theory becomes uncomfortable only when the same process is imagined on a planetary scale, preserving forms large enough for later observers to classify them as mountains. And scale is where the subject becomes most dangerous to accepted categories. We assume present biology sets the limits of past biology. We assume a tree must look like a tree we already know, only larger. But ancient Earth did not always run on current atmospheric chemistry, current gravity assumptions, current hydrology, or current ecological competition. The Carboniferous world already gives us oversized insects and vegetation, unlike anything alive now. The fossil record is full of abrupt limits in preservation and classification. Entire body plans appear fragmented, renamed, or misunderstood because only parts remain. If a biological structure exceeded later expectations by orders of magnitude, would it be recognized as biological once mineralized and broken, or would it be absorbed into the safer language of igneous intrusion, erosional remnant, and geomorphic anomaly? Consider the debris fields at the base of many isolated formations. The standard account says these are rockfalls, talus, collapsed columns, ordinary weathering. Often that is true, but look closely at the character of the fragments. Around some sites, the broken pieces are not smooth slope wash or rounded alluvium. They are blocky, elongated, angular, and concentrated near the perimeter, as if a coherent outer shell has been shedding in repeated sections. In petrified wood fields, mineralized trunks often fracture into segments with startlingly clean breaks, as though cut with tools. Park literature explains this by mineral brittleness and tectonic stress. Fair enough, quartz fractures cleanly, but the visual continuity between segmented petrified logs and column-shedding monoliths is difficult to ignore. One is accepted as former wood, the other is declared unquestionably not wood. The line between them is drawn less by form than by scale. Maps add another layer. If these formations were simply random leftovers of erosion, one would expect a broader spectrum of intermediate states, distributed more gradually across the landscape. Instead, many of the most arresting examples appear as singular or clustered monuments, set apart from surrounding terrain with an abruptness that feels selective. They stand like survivors. They read as remnants of a removed system. In some regions, flat-topped mesas and buttes occur in families, as if a once continuous upper layer has been cut into pieces. Geology says that is exactly what happened. Harder strata resisted erosion, while softer material vanished. But the eye notices something else. Those separated masses often resemble the broken crown fragments of something formerly unified in a vertical network rather than merely the leftovers of a horizontal sheet. The question is not whether erosion can isolate forms. It can. The question is whether erosion is the whole story. Early photographs are revealing in a quieter way. 19th century survey images of the American West, North Africa, South Africa, and parts of Australia repeatedly frame these formations with human figures at the base, and the scale does something unsettling. The landform stops behaving like landscape and starts behaving like object. Not scenery, object, an upright, bounded, singular thing. Many early observers lacked the later technical vocabulary, so they describe what they saw with blunt physical language: towers, posts, stumps, trunks, tables, petrified forests. This does not prove the theory. Common language can mislead, yet it records first impressions before professional explanations hardened into consensus. The record is still there. What changed was the explanation. Now, it is also worth noting what is often absent. If a formation is interpreted as the neck of an ancient volcano, where is the surrounding volcanic field? Sometimes it exists, at least in traces. Sometimes ash, dikes, intrusions, altered strata, or associated deposits do support an igneous story. Those cases should not be ignored, but there are formations where the volcanic context feels sparse, degraded, or reconstructed by inference rather than shown in intact system form. The explanation becomes circular. The evidence was once there, then erosion removed it. Erosion exposed the feature and erased the proof at the same time. That may be true. Geological time allows a great deal, but it is also the kind of explanation that can stabilize almost any anomaly by placing decisive evidence permanently out of reach. However, this is where the mainstream account is strongest and where it also begins to thin. Columnar jointing is real, measurable, repeatable in volcanic settings and visible in lava flows across the world. No serious investigation can pretend otherwise. If all we had were vertical columns, there would be little to discuss. But the theory does not rest on columns alone. It rests on the total pattern: isolated vertical mass, flared base, flattened top, debris ring, wood-like segmentation in related mineralized contexts, and repeated resemblance across multiple continents. Mainstream geology can explain each feature separately. What it struggles to do is explain why the same visual cluster keeps appearing in forms that invite the same forbidden interpretation. An answer that works piece by piece may still fail as a whole, and when the wider pattern is harder to dismiss than any single monument. Look beyond Devil's Tower and the famous examples. Look at truncated mountains with sheer sides in Tunisia, table mountains in southern Africa, isolated buttes in the American Southwest, stone pillars in Siberia, flat-crowned monoliths in South America, exposed petrified forests in Arizona, Egypt, Argentina, and elsewhere, coal seams compressed from unimaginable volumes of ancient biomass, silicified stumps preserved upright, basalt columns that resemble bundled fibers. The details differ, the composition differs, the histories differ, but the silhouette repeats. The pattern does not disappear. A civilization trained to classify by process may be overlooking a world that first needs to be classified by form. Once that possibility is admitted, other oddities move into view. Why are so many of these formations associated with language of extraction, cutting, quarrying, or exposure? Why do some crowns look planed? Why do surrounding sediments in certain regions resemble the sorted, layered aftermath of destruction rather than slow, uniform deposition? Why do some landscapes appear stripped, as if massive material once stood there and is now absent? Geology again has answers. Denudation, differential weathering, sediment transport, uplift, drainage incision. These are real processes. They shape continents. But the theory asks whether those processes may have acted upon pre-existing structures we no longer identify correctly, not instead of geology, before geology, or within it. There is also the problem of proportion. In ordinary forests, the relationship between trunk, branch spread, root network, and the surrounding ecology is constrained by available water, soil, atmosphere, and mechanical stability. We project those constraints backward and conclude that mountain-scale trees are biologically absurd. But that is a modern calculation applied to an unknown baseline. If the ancient biosphere operated with different pressures, or if the structures in question were not trees in the exact modern sense, but something functionally analogous, giant, conductive, mineral-rich growths, linking atmosphere, ground, and hydrology, then the objection loses some of its force. The theory does not need pines enlarged 1,000 times. It needs a lost class of vertical biological architecture whose remains would not fit our present vocabulary. That may sound like speculation because it is speculation. The question is whether it is empty speculation. As there are, after all, real precedents for biology and geology overlapping until the categories blur. Reefs become stone mountains, forests become coal basins, microscopic organisms build massive chalk deposits, shell beds become limestone, entire landscapes are made from accumulated life, then taught later as pure geology because the biological origin is too distributed to feel alive anymore. If microbial mats can shape sediment, and coral organisms can construct reef walls visible from space, then the idea that ancient life once created much larger vertical structures is not inherently irrational. It is only far outside the scale our textbooks have normalized. Institutional history matters here. Once a landform enters the survey record under a geological label, everything downstream reinforces that label. Park signs repeat it. Our schoolbooks simplify it. Databases codify it. Research funding follows recognized categories. A geologist who proposes an exotic intrusion model is still inside the discipline. A geologist who suggests a partly biological origin risks leaving the discipline altogether. That does not mean the truth is being actively hidden in some dramatic sense. Often it is quieter than that. Classification does the work, bureaucracy does the work, professional risk does the work, economics does the work. Accepted categories become filters. Data that fits them is accumulated. Data that does not fit is filed as visual coincidence, folk imagination, or fringe contamination. This is why the theory persists outside institutions rather than inside them. Not because it has been proved in secret, but because it cannot easily be tested without crossing boundaries that institutions are not designed to reward. To examine these formations as possible biological relics would require geologists, paleobotanists, mineralogists, structural engineers, and remote sensing analysts to ask a question most of them were trained to dismiss before phrasing it. Not, can erosion make this, but is there any measurable biological architecture preserved here that geology alone has overlooked? That is a different investigation. It would look for residue, patterning, isotopic anomalies, preserved microstructure, growth analogues, and fracture behavior not predicted by ordinary igneous models. Almost no one asks it. That absence matters. There are places where the silence feels louder than the evidence. Some monoliths are endlessly photographed, but rarely sampled beyond what is needed to confirm the accepted composition. Some are treated as solved because their rock type has been named, as though naming material also explains original form. But composition is not origin. Petrified wood is silica too. Quartz does not tell you whether the initial architecture was volcanic, sedimentary, or organic. It tells you what remains. The stone remembers, but not in plain language. Interpretation matters. A silicified trunk and a silica-rich geologic body can end in similar chemistry. The difference lies in structure, pattern, and context. That is exactly where the argument is still alive. Look also at terminology. A mesa is defined by shape. A butte is defined by shape. A neck, plug, stock, laccolith, and an intrusion are inferred by process from partial evidence. Some of these terms describe what is seen. Some describe what is believed to have happened. Once a process term is assigned, the shape becomes evidence for the process rather than an independent fact to be reinterpreted. This is not fraud, it is normal scientific compression. But compression can hide uncertainty. The official explanation for some iconic formations already contains hedges, perhaps a stock, perhaps an eroded laccolith, perhaps a volcanic plug, perhaps a Maya-related intrusion. In other words, the category is stable, but the mechanism is not. The confidence people hear often exceeds the certainty the record actually grants. The repeated resemblance to cut wood may still be accidental. That possibility has to remain on the table. Yet human perception is good at forcing familiar forms onto ambiguous objects. We see faces in clouds and animals in coastlines. Yet pareidolia is a weak explanation when the same interpretation emerges from geometry, fracture behavior, preserved wood analogues, and landscape patterning together. If one isolated butte resembles a stump, coincidence is enough. If dozens do, across scales and continents, coincidence becomes a habit of explanation rather than an explanation itself, and habits are not evidence. There is another reason this topic unsettles people. It reverses the direction of time we have been taught to imagine. We are comfortable with mountains becoming soil, forests becoming coal, reefs becoming limestone, lava becoming rock. We are less comfortable with the possibility that some features we call mountains may be the hardened corpses of things that once reached into the sky. It feels mythic. It feels pre-scientific. But the feeling is not the argument. The argument is that Earth preserves forms, and sometimes the form outlasts the explanation. What remains may tell a different story than the category attached to it. And if that sounds too grand, return to the simplest point. People stand in front of certain formations and, without coaching, say the same thing. It looks cut. It looks like a stump. It looks like wood turned to stone. Experts then explain why that impression is wrong, and often they are right, but not always fully. The eye is primitive, but it is not useless. Much of science begins with resemblance strong enough to disturb a settled account. Although the history of discovery is full of things first noticed as shape before they were understood as process. In this case, the shape has been noticed for generations. It is the process that keeps changing to protect the category. So no, the claim does not need every mountain on Earth to be a tree. It does not need to deny volcanism, erosion, or tectonics. It needs something smaller and more plausible. It needs only this, that among the landforms we have filed under ordinary geology, there may be remnants of a biological scale event the modern world no longer remembers. Some were mineralized, some were broken, some were buried, some were exposed and renamed. Over time, the names became reality. That is how forgetting usually works. Not with flames, with paperwork. If that is true, even in part, then these formations are not just scenic objects or geological curiosities. They are evidence of a missing chapter in Earth history, one in which the boundary between life and landscape was far less stable than we assume. Forest would no longer mean what we think it means. Petrification would no longer be a local oddity. And mountains themselves would become suspect, not as all one thing, but as a record we may have flattened into the wrong language because the right language sounded impossible. What changed was the explanation. The forms are still there, the photographs are still there, the survey records are still there. The isolated towers, the flat crowns, the flared bases, the segmented stone, the fields of shattered columns, to the repeated silhouette from one continent to another. None of it disappears because the theory is uncomfortable. Perhaps the standard account will absorb all of it in the end. Perhaps better data will close every gap and the mystery will shrink back into the ordinary. But at the moment, what remains is not certainty. What remains is a pattern, and once seen, it is difficult to unsee. A mountain becomes a stump becomes a question becomes a test of whether our categories describe the world or merely protect us from having to look at it again. The real question is not whether the theory sounds strange, but whether anyone with the tools to verify it has seriously looked.